Next, we will look at the concept of conditional probability. So, if we imagine a scenario where we can restrict the set of results of our experiment, or in other words, if we restrict the outcomes or the events to a subset of the entire sample space, then under this restriction, the probability of an event, which is also described as the probability of E given A, is known as the conditional probability of E given A, and it is denoted as P of E and A with a line sandwiched in between. Now it's quite clear that if we are restricting our results to a subset of the sample space, then the probability of an event, that is this conditional probability, is always greater than the probability without the restriction. Unless, of course, A corresponds to the entire sample space. So the probability must be normalized so that the probability that the condition is fulfilled is unity. What that means is conditional probability should have these properties. Probability of A given A should be 1, which is the normalization criteria. And probability of A2 given A1 the same as the probability of the intersection of A1 and A2 given A1. Now the probabilities might change with the restriction, but the ratios of probabilities should not. So P of A1 intersection A2 for A1 given A1, P of A1 given A1 should be the same as P of A1 intersection A2 by P of A1 when there is no restriction. And these requirements are met by the definition of the conditional probability of A2 given A1 equals P of A1 intersection A2 by P of A1, assuming of course that A1, the probability of A1 is greater than 0. Because if probability of A1 is 0, that means A1 never occurs. So asking the probability of A2 given A1 doesn't make any sense. Still, for completeness, we can define the conditional probability of A2 given A1 as 0 if the probability of A1 is 0. From the definition, it straightforwardly follows that probability of the intersection of A1 and A2 equals the probability of A2 given A1 times the probability of A1. So now let's consider scenarios where we can have more than one random variables. So in such cases, we can define some new quantities. First one is the joint probability distribution function. So if the outcome is more than one random variable, say x1 and x2, and the experiment is the sampling of a joint probability distribution function is given as f x1 x2, and just like the usual probability distribution function, this can be defined as the probability that the random variable capital X1 lies in the interval from small x1 to small x1 plus dx1, and at the same time the random variable capital X2 lies between the interval x2 and x2 plus dx2, and this is captured by this joint probability density function. Now if instead we have a finite interval, not an infinitesimal one, x1 lies between a and b, x2 lies between c and d, and that is given by an integral over both the variables. Another related quantity is the marginal probability distribution function. The marginal probability distribution function is the PDF of just one of the random variables. All dependence on the other random variable of the joint PDF is integrated out. So if we speak of the marginal PDF of x1, then that would be obtained by integrating the joint PDF with respect to the variable x2. Similarly, if we speak of the marginal PDF of x2, that is obtained by integrating a joint PDF with respect to x1. Now, just like we could define the conditional probability, we can define conditional probability distribution functions. So we assume that there are two random variables, x1 and x2. and the space of events is described by capital Omega. In the discrete case, the definition of conditional probability tells us f of x2 given x1, which is the probability x2 assumes the value x and x1 assumes the value, x2 assumes the value small x2, x1 assumes the value small x1. So this conditional probability is given by the ratio of the probability of capital X2 assuming the value small x2 intersection with capital X1 assuming the value small x1 divided by the probability that capital X1 assumes the value small x1. And that intersection is nothing but the probability that x2 assumes the value x2 and x1 assumes the value x1. We can identify the numerator as the joint probability density function. The denominator is the density function for the random variable x1. So for the continuous case also, these definitions are given analogously. So the probability density function for x2 given x1 is the ratio of the joint probability density function of x1 and x2 divided by the probability density function of x1 alone. Or, since we are talking about two random variables, f1 x1 is more accurately identified as the marginal PDF. Now from these density functions, we can compute the conditional probability. So again, the conditional probability that x2 lies between a and b, while x1 assumes this value small x1 is given by an integration from a to b over this conditional probability density function with respect to x2. And this quantity can also be written concisely. It's just like this. Now, based on these conditional probabilities and the conditional probability density functions, we can also compute conditional expectations. So the expectation for a function of x2 given x1, so again the integral from minus infinity to infinity of this function of x2 with respect to the conditional probability. Now the generalization to more than two variables is straightforward and it's based on a similar idea. So So let's say we have 4 random variables, x1, x2, x3, x4, and we want to look at the conditional probability density function of x2 and x4 assuming certain values, given that x1 and x3 assume these values. It's just the ratio of the joint PDF of x1, x2, x3, x4 and the marginal PDF for x1, x3. More clearly, the denominator f13 x1, x3 is nothing but the integration of the joint PDF with respect to x2 and x4. Now, as we discuss about experiments that result in more than one real number, that is, when we are concerned with more than one random variable and the PDF is of more than one dimension, it is important to understand that in such cases the random variables may not be independent, and we introduce the notion of correlation among the random variables. So this can be understood through a simple example. So let's say A is the event which describes that today is Sunday. B corresponds to the event that it is raining. Now, the probability of rain on a Sunday is the same as the probability of rain on any other day. Therefore, A and B are independent events. On the other hand, if instead of today is Sunday, the event A described the statement that we are currently in the month of July or in the month of August, then the two events A and B would not have been independent, because the probability of rain varies month by month. So if it said that the current month is July or August, the probability of rain would have been higher, and A and B would have been correlated with each other. Now, to get a mathematical formula for correlation, let's first look at that given a two-dimensional PDF, how do we define the mean and variance so the mean for the random variable x, or the expectation value of x, is given by, so we have to do two integrations. First, we have to do an integration over y so that we get the marginal probability density function of x, and then having obtained the probability density function of x, we multiply it by x and integrate with respect to dx. And similarly, the variance can be calculated as the expectation value of x minus mu x square. That's the second central moment. So a measure of the dependence of x on y is given by something known as covariance. So the covariance of x and y is defined as the expectation value of the product of x minus mu x times y minus mu y. where the mean of y can also be computed using a formula similar to what's given above for x. So if we do the multiplication and implement the expectation operator on that, what we get is something like this. Which ultimately comes out as the expectation value of the product of x and y minus the product of the means of x and y. Now, using covariance, we can define a dimensionless quantity known as the correlation coefficient. Is denoted by rho with x and y in the subscript, and this is obtained by dividing the covariance by the standard deviations of both x and y. Now we must note what happens if one of the quantities in the denominator is 0. So if the standard deviation of x is 0, and that means there is no spread about the mean, or that x corresponds to the mean. Therefore, expectation value of the product of x and y is the product of the mean of x times y, which is just a number, so it comes out, and expectation value of y is the mean of y. So therefore, in the definition of covariance, where we had a difference between expectation value of this product and the product of the means, so this quantity will be equal to 0. So the above definition of the correlation coefficient would give an indeterminate 0 by 0 ratio. So we simply define rho of xy equals to 0 if sigma x is 0 or sigma y is 0. Now, another property of the correlation coefficient is that it is scale invariant. Something which is not true for the mean or the standard deviation. Basically, if we multiply all the random variables with some constant number, and the mean as well as the standard deviation get multiplied by that same number. Now let's say we are looking at a scenario where the mean becomes 2 times and the standard deviation also becomes 2 times the original value. So we are only changing or modifying the mean and the standard deviation for the variable x, and we are leaving all the features of the random variable y intact. So in such a case, this rho of 2x comma y is the covariance of 2x and y divided by sigma 2x times sigma y. So the numerator is e of 2xy minus, so mu of 2x, mu of y, and denominator is 2 of sigma x, sigma y. From here we know that the product 2 into x into y, 2 is just a number, so it's constant, so it will come outside. And we also know that mu of 2x is twice of mu x, so the numerator is nothing but the denominator is similarly twice of sigma x, sigma y. So these factors of 2 cancel across the numerator and denominator, and what we have is just rho of x and y. The correlation coefficient rho of xy is a measure of how the variables x and y depend on each other. It is most useful when the contours of constant probability density, is contours for fxy equals k, are roughly elliptical, and in such cases we can make a straightforward assessment based on the shape of the contour or the orientation of the contour. Although this is not so useful if the contours have some non-elliptical or strange shapes. Example for something like this. Now, even though in the last diagram x and y seem to be related, but the correlation coefficient is 0. Now, a couple of things worth noting: that a change of variables can make rho from non-zero to 0. The second thing that we must understand is the correlation coefficient measures the average linear change in the marginal probability density function of one variable for a specified change in the other variable. Now, this change in the marginal PDF can be 0 even when the variables clearly depend on each other. So, 0 correlation does not imply independence of the variables. Now, let's look closely at the concept of dependence and independence. So we know from the definitions of conditional and marginal probability density functions that this joint density function can be rewritten in terms of conditional density function of x2 given x1 times marginal PDF of f1 just by inverting the relation. And the definition of marginal PDF tells us that f2 of x2 is just the integration of the joint PDF with respect to x1. So using the above two expressions, we can write f2 of x2, that is, we are substituting for the expression of the joint PDF in the integrand. Now, if This conditional PDF does not explicitly depend on x1. If it's the same for all x1, then this can be taken outside the integral. What we have is f1 of x1 dx1, which becomes equal to 1 by normalization, and what we get is f2 of x2 equals f of x2 given x1. If we resubstitute this in the expression for the joint PDF from the definition of the conditional probability, then what we can write is a joint PDF as the product of the marginal PDFs of the two random variables. So we can state that the random variables x1 and x2 are independent if the joint PDF can be expressed as the product of the marginal PDFs. On the other hand, x1 and x2 are dependent if the equality does not hold. Now, based on this, we can also derive the following theorem. So, if x1 and x2 are independent random variables, with marginal PDFs given as f1 of x1 and f2 of x2, then for functions u of x1 and v of x2, assuming all expectations exist, the expectation value of u of x1 times v of x2 is simply the product of expectation value of u of x1 and the expectation value of the v of x2. So let's compute and check if this is valid or not. So if you look at the left hand side, u of x1, v of x2, if we take the expectation value, that means we are multiplying these functions with the joint PDF and integrating with respect to dx1, dx2. But since x1 and x2 are independent, that means the joint PDF factorizes into the product of the marginal PDFs. So we simply get u of x1, f1 of x1, dx1 times v of x2, f2 of x2, d of x2. Now, we can supply an identity. So, or just the normalization criteria of probability. So but what we have done is we have simply just multiplied by 1 in both the integrals, and we have substituted for 1 in terms of the normalization of probability density functions. So then separately in the two integrals we can identify product of the marginal PDFs as the joint PDF. So this is f of x1 x2, and this is also f of x1 x2. In both cases we are integrating with respect to x1 and x2. So this basically becomes u of x1, the expectation of u of x1 times the expectation of v of x2. And because of this, we know from the definition of covariance that it's the product of x1 minus mu1 and x2 minus mu2. And now if we separately take the expectation values and then the products, so the first central moment is the expectation of this x1 minus mu1 is 0, because we take into account all the numbers and their differences from the mean, the average becomes 0. So for independent random variables, the covariance is 0. But as we have seen previously, the converse is not true.